Good day. Welcome to single phase motors lecture. Uh, we talk about general characteristics, construction, main and auxiliary winding operation, and the torque characteristics. General characteristics. Now, these single phase motors, they are not very high power motors, mostly used in home appliances and in portable machine tools. Excuse me. They need only single phase AC supply, and then small power rating, maybe up to 1 horsepower is possible. Low efficiency and low power factor. Inherent noise and vibration in operation due to the pulsating nature of power flow. So those are the general characteristics. Now the construction. It's very similar to a three-phase induction motor. Uh, they've got a squirrel cage rotor identical to rotor of a three-phase induction motor. Rotor is pretty much the same. Stator carries the main winding and also an auxiliary winding that operates during a brief startup period. Auxiliary winding has the same number of poles as the main winding. Now let us look at the winding arrangement. A typical 4-pole winding will look like this. This is the stator winding. Main winding has a group of 4 concentric coils connected in series. So it's the same coil but wound in to 4 different poles. And adjacent poles are connected to produce alternate north-south polarities. So if you carefully look at it, the winding direction has been changed. This one goes, say, clockwise, taken out. This goes counterclockwise, taken out. This again goes clockwise, taken out. This goes counterclockwise. That is to produce um, different polarities, north and south. And by that way, you can get an MMF distribution of this nature. And the empty slots in between, in the center of each pole, these ones, and partially filled slots in the outer circumference are used to lodge the auxiliary winding. Therefore, the auxiliary winding can be seen like this. So these are the auxiliary windings, position of auxiliary windings. So that is how the stator winding is done. So this is a 2-pole stator. If you look carefully here, this is the main winding. These two are the main windings, and then these are the auxiliary windings. Synchronous speed, exactly the same as the uh, equation for synchronous speed in a 3-phase induction motor. As in case of 3-phase induction motors, speed of the rotating magnetic field depends on the frequency of the supply source and a number of poles on the stator. Synchronous speed, of course, is ns is equal to 120 f divided by p. Fp and ns have the same definitions. Torque speed characteristics. Now if you look at the torque produced only from the stator winding, it will look like this from a single phase. If an AC voltage is applied with rotor locked, the stator will produce an AC flux. But since it is just one phase, it will pulsate. There won't be any revolving magnetic field. That's the tricky thing here. This flux will induce large AC voltage in stationary rotor. Will act like a short-circuited transformer secondary. Rotor will be like a short-circuited transformer secondary. If the rotor is spinned, it will continue to rotate in that direction. That is because of the slight lag that we introduce by force. It will accelerate to just below synchronous speed. So this shows you that if there is only the single phase winding, there is no way that the rotor can start its motion by itself. The rotating motion will not happen unless some outside intervention takes place. Now this is the practical problem. So how the principle of operation is like. You need cross-field theory, which is explained in 18 section 18 in the textbook. You can go through it carefully. As soon as rotor begins to turn, the speed EMF is induced, because when the rotor starts moving, there will be a induced EMF due to the speed of the rotor in the rotor conductors as they are cut stator flux. This voltage increases as the rotor speed increases. Now this causes rotor currents. The currents produce an AC flux that acts at right angles to stator flux. So there will be two flux components, stator flux and the rotor flux. They will be at right angles to each other. And rotor flux does not reach its maximum at the same time as the stator flux does. It lags by 90 degrees. So the combined action of the rotor and stator flux produces a rotating magnetic field now. So this is how the rotating magnetic field is sustained, but we still don't have a solution for the startup, and that is what we are going to discuss now. At the startup, a revolving magnetic field must be created. So we have to create it, as I said. Otherwise the rotor will not kick start. So to do that, what we do is an auxiliary winding is added to the stator. So this is the auxiliary winding with a switch. So remember, the auxiliary winding, the purpose of the auxiliary winding is to initiate the rotor movement and then drop off after the rotor picks up the speed up to a certain percentage of its nominal rated speed. So stator main winding and auxiliary winding will produce two fluxes that are out of phase, and this creates a rotating magnetic field. The phase shift between the main and auxiliary fluxes are achieved by adding an impedance, like could be resistive, inductive or capacitive, in series with the auxiliary winding. So this is the impedance purposely added to have a phase difference between the currents in the main winding and the auxiliary winding, so that the magnetic fluxes produced will be out of phase. Now it is possible to incorporate the desired impedance in the auxiliary winding itself. A special switch, this is the one I told you. Now that is a centrifugal switch which is mounted on the rotor shaft. So the centrifugal switch, what it does is, after it uses this centrifugal force to disengage. So after the rotor picks up, gathers the speed up to a certain percentage of its rated speed, the centrifugal switch disengages and cuts off the supply to the auxiliary winding to disconnect it when the motor reaches about 75% of synchronous speed. So that is how the startup is achieved. And then we talk about a couple of different types of single phase induction motors. Now the main winding, in case of a resistance split phase motor, has a main winding of large wire, low resistance and larger number of turns. And then the stator current considerably lags the voltage because of that. And then the auxiliary winding has fine wire, high resistance and smaller number of turns to achieve low resistance. Auxiliary current is almost in phase with the voltage. So auxiliary winding, in this case, this is the auxiliary winding, 70 turns per pole, number 22 wire, whereas main winding 120 turns per pole in number 16 wire. So therefore you don't need an additional inductor or a capacitor to be connected. That is how the difference in impedance has been achieved between the auxiliary winding and the main winding. You use windings of different gauge and different numbers of turns, and you got the centrifugal switch to cut off the auxiliary winding after a while. In case of capacitor start, auxiliary winding has almost the same number of turns as the main winding. See, the auxiliary winding has 120 turns here, main winding has 100 turns in 22 gauge, 120 turns per pole, 16 gauge, only 20 turn difference. A capacitor and a centrifugal switch is in series with auxiliary winding to keep auxiliary current leading by about 80 degrees. So when there is a capacitor, the current leads the voltage. This lowers starting current to achieve the same starting torque compared to its split phase equivalent. This causes less heating also. So this version needs causes less starting current and less heating. So capacitor start motor probably could be a bit better than the resistance split phase. And then the torque speed curve, it is interesting because in the beginning up to about 75% of the rated speed, the auxiliary winding is in circuit. So you got a non-zero locked rotor torque, and there is a pull-out torque just like in case of the three-phase induction motor, and it reaches the peak maximum torque, breakdown torque, and when it reaches here, the centrifugal switch opens. So the auxiliary winding drops off. So the torque characteristics now is taken over by the torque speed characteristics of only the main winding. So we drop down to here, and now this is the breakdown torque for the main winding, and down here is the normal nominal operating point. Power factor and efficiency of fractional horsepower single phase motors are low. They are very low in efficiency due to large magnetizing currents between 70 and 90% of full load current. So out of the full load current, magnetizing current takes about 70 to 90%. And the vibrations is the biggest headache with the single phase induction motors. The reason is because of the fact that there is this pulsating type torque power. So this is the supply voltage to the main winding. This is the current in the main winding. So if you work out the P VI product, which is the instantaneous power. Now like this section, the voltage is positive, the current is negative, so you got negative power, and then it jumps up because both quantities becomes positive in this sector, so you got a positive power, and then comes another small portion of negative power, and so on. Because of this pulsating electric power, the machine still have to deliver constant mechanical power if it is driving a load with constant torque. So because of this reason, it causes a lot of rotor vibrations. And now let us look at the overall motor construction. Now in this one you can identify, or I can show you all the different components that we were talking of. Squirrel cage rotor, of course, is this one, and main and auxiliary windings in the stator. These are the ones you can see, the sectioned windings. Centrifugal switch assembly for switching out auxiliary winding after motor comes up to speed is this little thing. This mechanism is the centrifugal switch. Built-in fan, shaft, bearing and motor case. Built-in fan is this one, obviously. The shaft is this one, rotor shaft. Bearing is, where is the bearing? Oh, that one. This is the bearing. And of course the motor casing or the housing is this, which holds this whole thing. So in summary, single phase induction motors are used in household appliances and portable tools. Auxiliary winding is needed for the motor to initiate the rotor movement. Rotor vibrations is a major limiting factor for having single phase induction motors of higher power levels. And thank you for attending this lecture.